today we are going to solve some example questions. Let me start with this one. So we have a circuit here. We have a circuit like this. Ooh, very complicated circuit. Maybe you have already solved this problem because it is in the physics department website. So consider the circuit in the figure with the capacitor initially uncharged and switch S closed at time t equals to 0. Find currents IR, which is this one, IR, IC, and IL right after the switch is closed at time t equals to 0. Do you understand the question? Does everyone understand the question or not? Yes. This is the battery.
Was there an initial charge at the capacitor?
There is no initial charge in the capacitor. Okay, it doesn't say so, but no initial current in the inductor before the key is switched on. Now key is switched on, turned on at t equals to 0, which means that we start like this. So let me ask you, what is IL? IL is 0 because okay, he refuses to talk today. Yes?
Because change in the current is very big, so it's will resist it so much.
Yes, very good. So L will act as inertia against this thing getting, like if you remember, we have an analogy of inductor. It acts like an inertia against current change, right? So at the beginning there is no current. Once we switch on this, the current will remain 0 over there. So IL is 0. And since IL is 0, all the current, it has to be the case that IR is equal to IC, right? And since the capacitor is initially uncharged, there is no potential drop there. Do you agree? Oops. That could be a good position for this, but let me bring it back. Okay. So no charge here, no potential drop here. The only potential drop is here, so IR must be equal to V, right? IR times R must be equal to V. Hence, IR is equal to IC is equal to V over R. Very simple question, which appeared in the final, I guess. Yes.
5 points.
No, this is 12 points.
Is this at t equals 0?
It is at t equals 0. Very good point. Then the question is, find the charge on the capacitor in the limit t goes to infinity. And that's it. Like there are two parts. Part A, 12 points, this, and you are done with this. Part B, charge on the capacitor. So that was part A. Part B is at t equals to infinity. What is Q? So how would you solve this?
There is no current through the capacitor.
Mm-hmm.
So IR equals IL, and it's equal to V divided by 2R.
Very good. So this time, let me just copy this. By the way, although the question is simple, the problem with simple questions is that you can make simple mistakes, which would take all of your points, right? That's the disadvantage of this. So you need to be careful with these simple problems. So at t equals to infinity, basically capacitors act as circuit breakers. Do you agree with that? They are fully charged. No current flows through them, right? And we are wondering what is the charge between these capacitor plates. So since all current flows through here like this, what is the potential difference between these 2 points? Let's find it out. Let's figure it out. Let's say this over here, let's say the potential over here is 0. Over here it is V, right? And then it decreases by minus IR over here, and it decreases again by minus IR. And over here, the current is settled, so there is no potential difference over here. Do you agree with that? So V minus IR is equal to 0. I is equal to V over 2R, which means that over here the potential was V, but after this we lose IR, which is I times R is V over 2, right? So you lose V over 2, which means that this point is V over 2 and this point is 0. So capacitor plates have a potential difference of V over 2. Did you follow this or not?
Why inductors potential difference is 0?
Very good question. Because current is settled, the potential difference over the inductor is this. Since this one is 0, you have no potential difference there at t equals to infinity, right? Any other questions? No? Well, you might mistakenly skip this question because it seems complicated, but you shouldn't do that, okay? Please make sure, read the question whether we are asking, because this is in principle an RLC circuit, and if we ask you to figure out the time dependence of currents and everything, then it's a very complicated question. But we are not asking that in this particular case. So the potential difference is V over 2. Since potential difference is V over 2, Q is C times the potential difference, which is V over 2. So Q is, at t equals to infinity, Q is CV over 2. So far, so good? Any questions, comments? Okay. I will solve another question from previous finals. Have you already solved this one? No. So it's useful for you. Another example question. From previous finals. This time there is a charge here, plus Q, and has a mass m. Starts with velocity v0 like this. This is 30 degrees. Okay, and there is magnetic field coming out. Okay, let's see. A particle with charge plus Q and mass m travels in a uniform magnetic field. At time t equals to 0, the particle has this velocity. At a later time t equals to t alpha, the particle will cross the x-axis at x equals to alpha. So there is this x equals to alpha. Okay, at t equals to t alpha, it will cross that point. determine in terms of Q, M, V0, B0 the value of alpha and the value of T alpha. Do you understand the question? The question is, what is alpha and what is T alpha? Okay. So Q, V cross B, right? V is pointing in this direction, B is pointing out. So I put my hand together with V, B is coming out, right? V goes like this, B is coming out. Okay, am I doing it right? Do you see? V cross B points this way. Let me show you here. F is pointing in this direction. What does it mean? It will make a circular motion in that direction. So it will go around, come back here, right? So we need to find that distance and that time, the time it takes. It's again those geometry problems. So if this is 30, then this is also 30, right? Do you agree or not? This angle is 90 degrees. This is 60. This is 30. Then this is 60.
Yes, yes.
Okay, this is also 60. Why that one is also 60? Yes, like this is R, this is R. It's symmetric and whatnot. Very good. So we have 2/3 of the full circle. 2/3 of the full circle. So let's find T alpha first. Let's remember mv squared over R was equal to QVB, right? So then R was mv over QB. Do you agree with this? And period was 2 pi R over V, which tells us that period is 2 pi. Do I have M over QB?
Yes.
Do you agree? So it does not depend on velocity, but we don't have all of it. T alpha is going to be 2/3 of this. Do you agree with this or not? Why it is 2/3? Because of the angle, right? This is 240 degrees, which is 2/3 of 360 degrees. Okay, so we have found T alpha to be pi m, 4 pi m over 3 QB. How about alpha? To find alpha, I need to use this R. So alpha is equal to, so I have R sine theta sine 60 degrees here, R times sine 60 degrees here, right? And R is mv over qb, so I have 2 times mv over qb times sine of 60 degrees. What was sine of 60 degrees? Root 3 over 2. So alpha is mv over qb with a root 3. So far so good? Everything is fine? No problem? Let's keep going. Okay. Another example. This one doesn't have a picture, so let me read it. A cylinder of length L and radius R is tightly wound by a copper wire making n turns. So far, did you understand it? Assume that the wire is wound tightly, so n is much larger than 1, and the cylinder is narrow, L is much greater than R, so that the magnetic field outside the solenoid is negligible. If the wire is carrying a current I, find the magnetic field inside the solenoid. It's something that we have done in the classroom, right? But in the final, you are asked to derive it one more time. Does it make sense? That's the first part. The second part is find the total energy stored by the magnetic field inside the solenoid, and finally find the self-inductance of the solenoid. Okay? So, for the first part, you can imagine currents going in at the top and currents coming out at the bottom, let's say. Okay, and we are assuming that outside the field is 0 and all the field is in here. Is it going to the right or to the left? Left, right? Left, isn't that correct? Yes. So, thank you. Then this length is L. So you use Ampere's law. You are basically using it like this. You only have one contribution. You have integral of B dot dl is equal to B times L. And it has to be equal to mu 0 times enclosed current, which is N times I. So B is equal to mu 0 N times I over L. Okay? Do you think this was pointless because we already did it in the classroom? No? It's fine? Yes.
I remember this. We write B instead of BL, we write 2BL.
Yes, very good point. So there are two ways of solving this problem. Okay? Did I discuss this with you? Yes. There are two ways to approach this. Either just like we did, in which case we didn't use superposition, right? But we already knew before using superposition that there is only a magnetic field in the middle, and outside it's 0. It's already given in the problem, all right? So far, no problem, right? The second way of doing it is the way that we did before in the class. In that case, we took this one separately. We solved it by itself, and while solving it, we assumed that there is a magnetic field here, there's a magnetic field here. Let me call it B prime. Okay, by itself. You understand?
Yes. Other side is
Then yes, exactly. Then you get 2B prime L equals mu 0 N I. And you get half of that, half of this B. So you get B over 2. But the thing is that when you do superposition, then you get such a situation. Look, you get B over 2 here, B over 2 here, and B over 2 here, while you get B over 2 from the bottom one, B over 2 over here, and B over 2 over here. Yes? So in total, it comes back to 0, B, and 0 again. Thank you. Is this clear to everyone? So this was magnetic field. How about energy density? Well, in the solution of this problem, the energy density was found in the opposite way. You remember we used 1 over 2 Li squared, okay, and found energy density to be this. But the solution of this problem starts from here, from this formula, and goes to the energy density expressed in terms of what you have. I hope this makes sense. Does it? If I give you L, then you write this energy density in terms of 1 over 1/2 Li squared and whatnot. If I give you geometric parameters, then you can use this formula, figure out B, and then UB is simply 1/2 mu over mu 0 times mu 0 and I over L squared. That's it. That's the solution. Do you understand this? Yes? This is part B. This was part A. And part C asks, it asks for L, and this time it asks for self-inductance. Do you remember the formula for self-inductance, the general formula? No? It was N phi over I, right? So what is phi? Phi is B times pi r squared. So you get mu 0 pi r squared N over L I. And then you divide this, you put this formula inside here, and eventually you get L equals to mu 0 N squared pi r squared over L. Okay? So far, my feeling is that finals are doable. Like, these questions are not that tricky. Maybe this one is tricky. Let me see. Okay. Yeah, this one is just a little bit tricky. So, in a circular region of space in the xy plane, there exists a uniform magnetic field with changes in time according to this expression. So, I have a circular region of space, and inside the magnetic field is B0 times 1 minus e to the minus t over tau. It points outwards, okay? It's only inside here. So far so good? And this is x, this is x, this is y. The question is, find the expression for the magnitude of the electric field at point A. Draw the electric field vector at point A on the figure. At point A is here. Find the electric field magnitude and direction. Can you find it? EA is what? So, what do you need to use to figure it out?
Change in magnetic flux.
Change in magnetic flux corresponds to integral of E dot dl, right? E dot dl is equal to minus d phi b over dt. So far, so good? So, this distance is r. I didn't mention that, I guess. E times 2 pi r must be equal to. So, with this minus, we will come to understand what this minus means. But let's first keep it plus, keep everything plus. So, for this case, negative of the differential. So what do I get? B0 over tau, and I'm going to take just the plus part of it. Okay, I will make it plus. Or is it okay if I make it just plus and find the magnitude? Yes. Okay. Okay. Let's talk about the exam and let's not change it. So, for this negative sign actually tells you something, right? What does it tell you? It tells you the following. So, you have a magnetic field that comes out of the page, and this corresponds to curling in this direction. Okay? So if you get a plus sign from the right hand side, there should be an electric field in that direction. Did you get this? If the right hand side gives you plus, then E times 2 pi r is equal to that value, and it should be an electric field going like this. But if you get a minus, then it should be going on the other direction. That's what it means. Okay? So let's see what the right-hand side gives us. The right-hand side gives us minus of this minus. Okay? And then I have the derivative of 1 gives me 0. I have a minus because of the minus in front of the exponential. I have a third minus, so this is a second minus. Then there is B0. Then there is minus 1 over tau times e to the minus t over tau. Did you follow this? Yes? So the right-hand side turns out to be negative, B0 over tau, e to the minus t over tau. And this minus tells you that the electric field must be clockwise. Okay?
Can we also say that magnetic field is decreasing?
Exactly. That's another way of doing it. Let's do it that way as well. But let's first finish with this one. So this whole thing, B0 over tau, e to the, let me finish, then let's, just this part.
The problem is you forgot
I totally forgot A. Thank you very much. Pi r squared here. Okay? Thank you.
A.
Where it came from?
It's magnetic flux, right? E times 2 pi r. Pi's go away, r's go away. You get E is equal to B0 over 2 tau e to the minus t over tau. And it's clockwise. Let's also decide on clockwise.
One of the R's is forgotten.
Yes, where is that R? Over here. Okay. Let's go with your logic. So you are saying that magnetic field is decreasing. Is that correct? Is it decreasing though? 1 minus e to the minus t. It is actually increasing. Do you see that? The magnetic field is actually doing this. it's going towards B0. So magnetic field is outwards and it is increasing, and the response must be inwards. So the response is generated by an electric field that points in this direction, right? Like it has to curl this way, just like we have found it, right? So in particular, EA is pointing in the positive x direction. So EA is going to be B0 R over 2 tau e to the minus t over tau times I direction. Okay? Are you happy with this? Yes. The formula for magnetic field is this. It's given by the problem. And when t is 0, 1 minus e to the minus 0 is 0. When t is infinite, e to the minus t is 0. 1 minus 0 is 1. So it is increasing. Any other questions? No questions. So the second part is out of the scope, so I will skip it.
What was the second part?
Something about pointing vector.
By the way, I couldn't find these questions because I printed out the finals. But
This is different?
No, no, same.
Same?
There is existing.
Exercises mi?
Yok ya, çıkmış yani.
Şimdi çıkmış sorular var, bende yok o soru.
Okay. Let's look at this question. Consider a coaxial cable whose inner conductor is a thin hollow tube of radius r1 and outer shell is also a thin hollow tube. So both of them are thin hollow tubes. One of them is R1, the other one is R2. The question is, part A asks you to find capacitance per unit length. Let me C over L. And second part asks you to find inductance per unit length. Do you understand the question? Yes? So for the capacitance part, you basically give plus Q inside, minus Q outside, and find out the potential difference. Do you remember how to do that, or did you forget? Maybe you forgot. So let's do it. At any arbitrary radius r, if you think of a Gauss's surface, then E dot this surface integral needs to be Q enclosed over epsilon 0. So E times 2 pi RL is equal to Q over epsilon 0, right? How about the potential difference? The potential difference will be related to the integral of this. So delta V is going to be integral, and I don't want to run into negativities, so I think if I go from R1 to R2, integrate the electric field, 2 pi epsilon 0 L times R dr will give you the potential difference, right? So what do you get? You get ln R2 over R1. Now, you know delta V. How do you derive C? Q over V, Q over delta V, which is going to be 2 pi epsilon 0 L over ln R2 over R1, and that gives you C over L if you take L to the other side, right? This is capacitance. How do you find inductance? Do you remember what to do with the inductance? Let me remind you. For the inductance, you need to know n times phi over I. And in this case, n is going to be just 1. We consider the whole outer tube. Let me think. So the way that we think about it is this way. So you have a tube like this. Let's say there is I coming out of here and I going in here. That's the way we think about it, and it's going to create a flux inside this, okay, and we need to integrate that flux. Okay, so let's first find the current, the magnetic field, sorry. So at a distance r, B dot dl must be equal to mu 0 I enclosed, right? Then B times 2 pi r is equal to mu 0 I. So we have found the magnetic field. How about the flux? The flux will depend on this area that is perpendicular to this magnetic field. So at a distance r, you have this dr, and we are going to integrate that area, that flux area. Do you understand this? So we have d phi b is equal to b times dA, which is b times L times dr. Is that right? So you get the whole phi to be integral mu 0 I over 2 pi r L dr. Same integral, do you see? Gives you same integral. So you get mu 0 I over 2 pi, and there's L here, ln R2 over R1. So to find the inductance, you need phi b over I. And to find actually inductance per length, you need to divide it by L2. So you get mu 0 over 2 pi times ln R2 over R1. Why? Okay, no problem, right? Do you have any questions?
Why did we take L times dr instead of the
2 pi RL.
iron?
Yes, because look, in this case, we are interested in this magnetic flux that goes inside that surface. So this is the magnetic field. This is the magnetic field, and it penetrates. So if you look at this section, it's a cut from a cylinder, and if you cut a cylinder, it looks like a rectangle. And on this section of that rectangle, we are interested in flux, because as you go away from the center, the magnetic field changes. Okay, so you have a certain amount of flux here, a certain amount of flux here, a certain amount of flux here. So you integrate those small fluxes. And what you see as a section is L times dr. Okay? Yes.
Can a similar question be asked for a spherical system?
Not really, because for a spherical system you can talk about capacitance, but not, I mean, can you make a sphere and would it have an inductance? Yes, it will, but it's not what we ask in the exam. So far, so good? Okay. Let me continue with this question, next question. So in the next question, we have like a rail here. And there is a rod that has a mass m and resistance r, and there is magnetic field pointing up, and this angle is theta. We take into account gravity for this problem, and this distance is L. Do you understand the system? Maybe I should draw it with a different color. This is a rod. Okay. A conducting rod of mass m, resistance r, is placed on two parallel conducting rails with no resistance, inclined at an angle theta with horizontal and connected to each other by another resistanceless rail at the bottom. Assume that there is no friction between the rod and the rails. Throughout the region, uniform magnetic field exists in the vertically upward direction. The rod starts from rest and slides down the incline under the action of the gravitational force. What will be the direction of the current, induced current? Do you understand the question? Very nice question. So what's happening here?
Rod is sliding and magnetic flux is decreasing.
Yes.
So there will be induced currents in clockwise.
Yes, very good. Very, very good. So, let's see. So it's going down, and while it's going down, it's reducing this area, right? So it's reducing the flux that is coming out, right? Now, there is a flux going out, and it's being reduced. So the net effect is actually down, right? So the response must be up again. So the current must be flowing in this direction. Does everyone agree? So the current will be flowing in this direction because of the induced, because of the Lenz's law. What will be the terminal speed? Do you remember terminal speed? Let me just remind you. Let's say you have a parachute going down. There would be a drag force. Was it proportional to v squared? Sometimes it's proportional to v squared. Sometimes v to the 4, sometimes v. Like, make your mind, right? Anyways, whenever mg is equal to whatever the expression for the terminal velocity is, you get the terminal velocity, right? Terminal velocity is the velocity when it stops changing. So in this particular case, as it goes down, there will be current induced, in this direction, but B is pointing up, which means that there will be a force L cross B in this direction. Do you understand why? Current goes like this, B goes like this, up, right? L cross B is in this direction. So if we look from the side, there is a force I L cross B in this direction, and I and B are perpendicular, right? I'm talking for the rod, just for the rod, not the rails. Okay? And then there is mg in this direction. So the component of mg in this direction and the component of F in this direction must be equal to each other. This is theta. That is when we will reach the terminal velocity. Okay. Do you need a break? Would it be awkward to stop here? No? Let's have a break and continue next hour.